Okay, so this is the video lesson for 4.1 exponential functions. We're just going to start out with some basic applications of exponential functions, and then we'll get into the specifics. So this first example says an infectious disease begins to spread in a small city of population 10,000. After T days, the number of people who have succumbed to the virus is modeled by this function. Now this is actually very much a transformed exponential, there's actually another name for this, a logistic, because the e, or the exponential part, is in the denominator, which is going to really transform the end behavior of this graph from a regular exponential. We're going to get into graphing and how to do all that stuff by hand later. Right now, let's just answer these questions, but I did kind of want to point out that this is not just your standard exponential function. All right, so how many people are initially affected at time t equals 0? So this is where we're just finding v of 0. Now, if you think about it, you can do this one by hand because e, the natural number, which is associated with natural log, that is a number. So when I take it to times 0, e to the power of 0, that's just going to be a 1. So I could actually do this one by just dividing 10,000 by 5 plus 1245, or that would be 1249. Oh, whoops, not 1249, 1250. And that gives me exactly 8. Okay, so I would say 8 people. Now to start doing the other ones, we are going to have to use the calculator. It's just too difficult to do this by hand. It would take a lot of calculations, and nobody in their right mind would want to do this by hand. Okay, so first let's go ahead and let's plug this into our calculator and let's check that first answer. Now when you type this into your calculator, you want to be careful to make sure that the whole denominator is in its own set of parentheses. You also want to make sure that you use the natural number e, and notice that it does e caret and it opens up its own set of parentheses. We're going to do negative 0.97 x for t, and if I go to the table, I can confirm that at time equals 0 there were 8 people infected, and now I can answer all the other questions. After 1 day, 21 people were infected. You're just going to have to estimate here because it's probably not going to be an exact number. After 2 days, we'll say 54 people were infected. Okay, what was the next one? 5 days. So we'll scroll down, and we'll say after 5 days, 678 people were infected. Now there's definitely argument to round up or to round down, okay? I would say you don't need to round up unless it's really close to that next number. If it's about halfway, just round down, okay? We will talk more about that though in class, okay? So our v of 1, when that was rounded, that gave us 21 people. You definitely don't want to leave it as a decimal. That doesn't make sense in the context of the problem, meaning our x value, or our y value, is number of people. Our v of 2, the number of people who had the virus after 2 days, that was 54 people. And then our v of 5 was 678 people. Okay, so then it says, well, when will 1,500 people be infected? Now there's a couple of different ways we can do this. Again, we can go to the table and we can estimate at least. It looks like on the 7th day more than that. So we could say between 6 and 7 days. That would be one way to answer it. So let's go ahead and write that down first. This is not a bad way to answer it. Now, if you want to get more specific, especially if this wasn't talking about days, but if it was talking about years, you would want to be more specific. Even days, you might want to be more specific. This is when we're going to go into the graph. Now, you can see here that our domain of our problem would be however many days it takes for the whole population to become infected. Okay, now it looks like that's not going to happen, and that's the interesting part about these logistic functions. They balance out. It looks like it's balancing out to 2,000, so we'll go out to 15 days and 2,000. Okay, so we'll go 0 to 15, and then again we'll go 0 to 2,000. You might want to, we could maybe go a little bit more just to see the top of that, 2,200. And this makes sense when you think about disease. It'll level out. Because people will gain immunity or it'll be squashed. That's how diseases happen. That's how they go away. So if we want to find the answer to part C exactly, when will 1,500 people be infected, we need to type in 1,500. This will give us a horizontal line, and we're going to find the intersection. That'll give us the time. Now we know it's between 6 and 7. Find the intersection exactly. That's going to give us 6.821 if you want to get real specific. Okay, so we'll say when t equals 6.821, and that's in days. Okay, so we already graphed the function to kind of get more specific on C. Let's go ahead and make our own graph right here, a sketch. Okay, so remember that we started with 8 people, so it doesn't start at the origin. It actually starts about right here, and it looks like it goes up, and then it kind of levels off. All right. One thing that I want to note here, let's label, this is T, this is V of T, and let's describe the end behavior. As T approaches infinity, what is V of T approaching? We kind of already said it's the level off, 2,000. And that's like another asymptote here, horizontal. So this is what I'm saying. This is not your standard exponential, but it's a good place to start in this chapter because it's the easiest way to actually apply this stuff to a real-world situation. Okay, now let's talk about compound interest, and I'm going to go over this pretty quickly because this should be gone over this several times now. There's 2 formulas here. One is for interest that is being compounded so many times a year, and this one is a continual compounded. So when you see compounded continuously, you use this A equals PE to the RT. This is an interesting formula because we're going to use something very similar to it when we get to half-lives and doubling and bacteria in a petri dish and all that kind of stuff. All right? So let's go through what each of these things mean. And you write down whatever you need to write down. A is your current, or you could say your final amount. Okay? P, that's your principal. That's how much you start with. All right? So however much money you put into the bank account. R, that's going to be your rate. It will be as a decimal. So a 5% rate would be 0.05 for R. N, here and here, this is the number of times per year your interest is compounded, and T is your number of years. All right, so write down, rewind, write down as much as you need to. You can Google and they will have all this written out for you as well. I'm not going to do that though. I'll do that within this problem. So 2 says, how much money would you have if you invest $1,000 for 3 years at an interest of 5% compounded weekly and continuously? So the weekly part, we're going to use the first formula. So I want to know what is the amount of money, the current or final amount of money, if we invest $1,000, so that $1,000 is our P, at 3 years, which is our T, and again our interest rate here is going to be written as a decimal. Now compounded weekly, how many weeks are there in a year? There are 52. So this N is the number of times the interest is compounded in a year. The more often, the more money you will make. So let's do parenthesis 1 plus 0.05 divided by 52, and we're going to take this to a 52 times 3 power. So let's figure this out, and on these problems you are going to want to round to 2 decimal places because it is money. So we're going to, we don't need that. We're going to go here and we're just going to calculate it. Now these do get a little bit more difficult when they're not asking for A, but they're asking for P or for R. And we'll just kind of work at those as they come along. One thing I do want to point out here is that you have to put parentheses. If what's after the caret is more than just a number, if it's an operation like this, 52 times 3, you have to put that in parentheses, because the power needs to be the total number of times this interest is compounded. So it was 52 times a year for 3 years. All right, so then we get 1161.75. Okay, so that's not bad. All right, now let's do the continuous one. Okay, I'm going to do this one in red. All right, so this is going to give me, you know, the P is still the same number. There's no N to worry about, but notice that we have this E again, the natural number. It has a lot of applications, and this is just one of them. Our R was 0.05, and our T was 3. Okay, there's no N because it's compounded continuously. Okay, so let's type that into our calculator. 1,000 E, and again, use this E down here. It'll automatically open the parentheses after the caret, which is nice. And notice that it was just a little bit more. May not seem like a big deal. It went from 75 cents to, we'll say, 83 cents. So let's write our answer down. A equals 1161.83. This may not seem like a big deal here, but if we're talking millions of dollars, this really could make you a lot more money. Okay. So again, continuously just means all the time. More often you compound an interest, the better. So continuously under the same rate and time and all that, it should always give you a better outcome. There is no bank that does more often than compounded weekly. Besides the continuous, there's no compounded daily or anything like that. If a bank wanted to do that, they would just use continuously. And really, most bank accounts I see aren't even weekly. They're monthly or, you know, biannually, things like that. Okay, bring your questions to class and make sure you have a working calculator because you're going to need it for this section.